Hello, good evening. Welcome to the fourth week's online tutorial session on Introduction to Mechanical Vibrations. My name is Parth Joshi. So I am currently pursuing PhD at IIT Bombay in the Department of Mechanical Engineering, and I am a Prime Minister's Research Fellow. And as a part of my fellowship, uh, I got this opportunity to interact with all of you and conduct these online weekly tutorial sessions. So, welcome again. So, I thank NPTEL for giving me this opportunity uh, to share my learning about the vibrations course with you. And yes, and I thank the PMRF and NPTEL team for giving me this opportunity. So, till now we have in this course so far we have seen concepts related to free vibrations with and without damping, and we have also looked at uh, vibrations of systems with in which there is some harmonic forcing. So uh, in the last week we saw how like the forced response of the system to forced vibrations. So when damping is present in the system and when damping is not present in the system, and depending on the level of damping, the system behavior also changes. So we saw the concepts related to like the how the system behaves when the system is under damped, over damped, or when it is critically damped. So in this week, we would be basically looking at the problems related to concepts with in which we find out the equivalent damping present in the system. So there are other types of damping like Coulomb damping, structural damping. Those have been covered in the content related to this week. So we would be uh, in this week's content focused on how to find out the equivalent viscous damping when there is Coulomb damping present in the system or structural damping present in the system. And when we want to, when there are forced oscillations, uh, and if we want to avoid any undesirable vibrations, we design a vibration isolation so that the amount of force that is transmitted to the system that is minimized. So for example, if a machine is resting on certain foundation, and that when there are oscillations uh, present in the surroundings which may cause some disturbance in the existing machine. So in order to avoid that, we design a vibration isolation so that we reduce the amount of forces that are transmitted to the system. So there is a term called force transmissibility, which measures the extent of forces that are transmitted to the system, to the foundation. So if there are certain, if there is some, uh, let us say, rotating unbalance present in some machine, and if you want to, let us say, quantify the uh, fraction of the total forces or magnitude of the total forces that are transmitted to the foundation in comparison to the total force that causes the excitation, then we define the term called force transmissibility. And there is another concept of motion transmissibility where let us say if there is some the base of a machine, let us say it there are some oscillations caused because of which some forces are transmitted to the machine through the base when the base itself of the machine itself is moving. Hello. Hi. Hi, Bhavna. So thank you for joining this session. So, Bhavna, thank you for joining this session. So my name is Parth Doshi. So I've been conducting these weekly tutorial sessions for this course since the last 3 weeks. So, and I am basically a PhD student at IIT Bombay, and I am conducting these tutorial sessions as a part of Prime Minister's Research Fellowship. So just wanted to know a little bit, it's like, have you watched the videos of the earlier tutorial sessions by any chance?
Yes, sir.
Can you please unmute and speak?
Yes, sir.
Sorry, cannot hear you. Yeah, can you please unmute and speak? Okay. So, so Bhavna, where are you from? Can you please just briefly introduce yourself? Like, where are you from, and what are the like? You are from Chennai. Okay. So, are you an undergraduate student, or like, can you just briefly tell about yourself? Are you a B Tech student, or B Tech or M Tech, or what? Okay. So, you are a B Tech student, right? So, in which year are you studying? You are going to second year. Okay, fine, fine. So are you able to understand the content related to this course?
Yes, sir.
Okay. So because I
No,
think you have just completed your first year of mechanical engineering, so some of the concepts they might not be, completely familiar.
yes, sir. That Fourier series. But
4 year series. Okay. So you have any questions related to that? You have any questions related to that the concept of Fourier series?
1 minute, sir.
So if you have any particular question or anything, like if you want me to explain something related to that, so you can let me know that. So I'll try to explain whatever I know related to that.
No, sir.
So you said like Fourier series is not clear to you. Is that so?
Yes, sir. During that beach phenomenon,
Beat
uh,
phenomenon. Ha, so
I
beat
think
phenomenon. So yeah, let me.
uh, both have similar frequency,
Yes.
near frequency.
Yes, so this was yeah, yes, when two, like there are two, let us say some two like vibrations that are um, like for example, when there are two vibrations which are, operating at, let us say, two systems, that those are oscillating at two different frequencies, and their frequencies are somewhat similar or very close. So, for example, if how to understand this phenomenon of beats like in normal life. So you might have observed like when tuning like musical instruments. For example, do you play any musical instruments or have you listened to any like music? Uh, like, do you play any musical instruments?
No, sir.
Okay, fine. So basically, like if you want to tune like musical instruments, like let us say guitar or any string instrument or whatever. So, what do they do? Like they generally play some reference sound, which is of some reference fixed frequency. And while let us say if you want to tune a guitar string, what they do is they will tighten the knob of the one end of the guitar string. So, and they will increase or decrease the tension in the string. So, what
Hmm.
will happen is that the natural frequency of the string will change. And when you plug the string and as you tighten the knob of the string, then the frequency of oscillation of the string will change. Now, while tuning, the reference frequency is always at like is fixed, and when the frequency of vibration of the string, when it comes close to the reference frequency, then you can actually hear the sound like the beats phenomenon. What happens is that then you will see uh, the sound like the amplitude of the sound goes on increasing and decreasing. Like you will see ting 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 ting, ting and it like the whatever you will be able to hear that sound. It the the intensity of the sound initially increases and then it again goes on decreasing. So you will be able to hear that. So if that's why I asked like whether you have experienced this kind of thing. Uh,
Hmm.
so there you can actually hear the sound of beats, and once when the two frequencies will match, like when the string of the like the vibration, the frequency of the string, when it matches the reference frequency, then you there will be resonance, and there you will just hear one single sound and a loud intensity sound. So that is when the beats phenomenon is eliminated. So beats phenomenon means that the amplitude of the oscillation goes on increasing periodically and decreasing. So there are like kind of like let us say if there are two frequencies, then uh, there is one oscillation which goes on continuously, and the amplitude of the oscillation goes on increasing and decreasing continuously. So like if you have a constant sine wave, instead of that you have another one sine wave inside another sine wave. It's like that. So the there are like if you see a picture of the if you want to see the the picture
Yes.
of how a
So
signal
the
which
phase diagram, it would be one would be small, one would be big.
sorry.
The phasor diagram, that circle,
Ha ha ha.
in that the amplitude, the what would be the size of both? It would be different, or
Ha, just a moment.
how the phase difference would change continuously and
Yes, just a moment. Uh,
yes.
so are you able to see this
Yes, sir.
figure over here? So this is the figure which explains the phenomenon of beats. Uh, like when there are two sine waves which are like oscillating, which are interacting, and their amplitudes are equal. So you can see that the amplitude of the oscillation, the reason like the net oscillation, it actually uh, goes on. There is one bigger sine wave which, and there is another sine wave which actually goes inside that. So now, like regarding the like the thing of about phase difference which you were asking, so that this part, like this concept, right? So there is one vector OP1 which is rotating at angular velocity omega, and the other one which is uh, rotating at omega t plus phi,
Yes, sir.
right? So here the amplitudes, we are assuming them to be equal, so then it is easy to write down this expression and get this thing. But in general, when uh, we want like to like the resultant, the sum of the two sine waves, if we want to represent, like let us say this x1 plus x2, when they are like have some general amplitude and phase difference, so it's kind of difficult to write it down in this way. But what happens is that the like let us say this, um, if you add these two vectors, then the vector sum will be somewhere.
Hmm.
And see here, you are assuming that this vector x1, like it is rotating at some angular velocity omega 1, and the other one will be rotating at some angular velocity omega 2. Now let us say this is the snapshot of this circle. So
Yes.
here in this case, if the angular velocity omega of both is same, then if you add up these OP, the vector sum of OP1 and OP2, it will be one vector, and the phase difference between them will remain constant, right?
Yes, sir. Yes.
Right. So now, but if we have two vectors, let us say OP1 is rotating at, let us say omega 1, and the other is rotating at omega 2, then what will happen is that the angle between OP1 and OP2 will keep on changing with
Hmm.
time, right? So if suppose, for example, to let us say P1 and P2 are like two let us say like there are two, assume a running race kind of thing. So two people start at the same point of time, and let us say if they are running around this circular track with different speeds, then the distance between them around like basically the around along the arc, that will keep on changing with time, right? So
Yes, sir. Yes.
at some time they will meet, and at some point they will be far apart.
Sir, and in the middle also it would be difference. So in the middle of the,
Yeah,
it will be A minus B.
right.
Sir, or only when they are far apart, it would be A minus B.
Yes. So at some point of time they will be far apart. So the net amplitude will be A minus B, and when they are, actually when they are actually coincident, then the net vector addition will be A plus B, and when they are 180-degree
Yes.
opposite, then their net amplitude will be A minus B, right?
Yes, sir.
So are
Yes,
you
sir.
able to visualize? So I can also explain using a whiteboard. So let me just.
Yes, sir, I can understand it.
Yeah, so just to clarify what I'm saying, I'll just uh, so can you see my whiteboard?
Yes, sir.
Yeah. So what I was saying is that, so if let us say this is, so this vector is omega 1, rotating at omega 1, and the other vector op2, let us say it is rotating at vector omega 2, so the angle between them, so this theta 1 is basically, let us say, omega 1 t, and this theta 2 is basically omega 2 t. So this phase difference will be dependent on the uh, it will basically depend on the uh, difference between the two angular velocities. So when, so at some point of time, it they will be the phase difference will be zero, and at some points it will be actually 180 degrees. So when the phase difference is zero, then the net amplitude will be basically sum of the two amplitudes, so OP1 plus OP2. And when they are 180 degree out of phase, then it will be OP1 minus OP2. So
Yes,
does that answer your question?
yes, sir. Yes.
Okay. So any other question?
So can you also explain the time period of the beats, that wave representation?
So the time period of the beats, this part. Uh,
Yes, sir.
yeah. So when we basically add up these two sine waves, x1 plus x2. So and let us say if their amplitudes are equal, then we can write them as cosine of omega t plus cosine of omega t plus delta t. So uh, using this identity of cos A plus cos B, so we can write it as cos of like A plus B by 2 into cos of A minus B by 2.
Yes, sir.
So it becomes basically a product of two sine cosine functions. This addition of x1 plus x2, it becomes like a product of two cosine functions. So one is varying at with 2x cos delta t by 2 into cos of omega plus delta t by 2. So the inner sine wave is basically like equivalent to it is actually oscillating at frequency omega itself. And there is another sine wave which is uh, kind of basically you can like instead of saying that this is like some a cos omega t and this
Yes.
a is a function of time. So this the amplitude of this whole sine wave, let us say you can write this as, let us say you write 2x cos delta t by 2 as some a1, let us say. So x of t is a1 cos omega t plus delta t by 2. So that
Yes.
a1 is varying with time. So
Hmm.
the frequency with which a1 is varying with time. So that basically is depending on the phase difference between those two signals. So that delta, it actually represents like the phase difference, right?
Oh,
So that's how like you get that time period.
but sir, we have delta t by 2. So,
So because that's what I like just said that this delta this
oh,
delta thing, it actually depends on uh, it is like basically omega 2 minus omega 1, just what I just explained on the whiteboard. So that delta, it is basically omega 2 minus omega 1.
yes, sir. So then omega is equal to delta by 2. It should come now, sir.
Omega is not delta by 2, it will be, let us say here, see here x1 and x2 are like uh, having the same frequency. So this omega plus delta is basically the frequency of the other sine wave. So
Yes,
let us
sir.
say so we can write omega 2 as omega plus delta, and omega 1, let us say we call it as omega only.
Yes, sir.
So delta is basically the difference between the two frequencies,
So,
and the phase difference will be that difference omega 2 minus omega 1 into time.
hmm. So here, if I take this x of t as a cos omega t, general wave equation,
Sorry.
this x of t
Haha.
as a cos omega t as general wave equation.
Haha.
So then a is equal, as you said, 2x cos omega t by 2.
Haha.
And this is cos omega t,
Yes,
where
yes,
omega omega
yes.
plus delta by 2. So then 2 pi by omega is the time period. So it should be 2 pi by omega plus delta by 2. No, sir.
uh, no, so here we are talking about this part, like the the first like the 2x cos delta t by 2. So that has a time period of 2 pi upon delta by 2, right?
Yes, sir.
uh, does
So
it make
both
sense?
are,
Huh?
so this is amplitude or this 2x cos omega t by 2.
Yes, yes. So that is like amplitude of the one sine wave superimposed onto another. Like it's like if you can visualize that. So if you look at this figure, then you can actually clearly make out like the outer sine wave is basically 2x cos delta t by 2. It's shown over here. So uh, the time period of beats here is basically 2 pi upon delta. Does that make sense?
That it should be 2 pi by omega plus delta by 2, no, sir. That only.
No, that is basically the this sine wave which is inside.
Okay, sir. Okay.
Okay, right?
Sir, but both should be same, no, sir. This should be half of the time period inside.
What should be half of the time period?
This outer sine wave
Haha.
should have greater time period than this beat period.
Yeah, that is the case, right? So this outer one is lower than the inner one, right? So the inner sine wave is actually oscillating at a greater frequency, right? It is completing more number of cycles, whereas like if you see this time
Yes.
period is actually longer, right? So
So that would be double of this beat period, no, sir.
what will be double of that?
Sine waves time period.
Ha, yes, it will be double of that.
But that formula, it is saying it should be 4 pi by delta.
No, 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 because see, because like this thing, uh, see, this is the kind of because of its symmetry, it's actually it becomes actually half of that because this thing, see, this pattern is actually uh, repeating two times, like in one cycle itself. Like so, uh, the time period of this sine wave, you are right. So it should be 4 pi by delta, but this these the sine wave which is like you can kind of assume it like uh, two sine waves are like being superimposed onto each other. So this pattern is actually you can say that like it appears twice in one cycle. So that's why it actually becomes half of that.
Yes, sir. But in the previous x of t formula,
Yeah,
so we are not getting that same time period, no, sir.
x of which x of t formula?
This x of t wave equation.
Uh, I don't actually and didn't get which formula you meant.
Yes, sir. This only.
This one,
Yes, sir.
1.67.
1.6. Yes, sir. This 2x cos of delta t by 2 cos whole of omega plus delta by 2.
Yes, yes. So see, if you just plot 2x cos delta t by 2, that will be just let me just give me a
So
moment.
that is the amplitude of that outer sine wave.
Ha, so that is the amplitude of the outer sine wave.
And this cos omega t or omega 1 t is
Just a moment. So you are basically talking about this equation, right?
Yes, sir.
So let us say if we separately just plot this thing, it will be uh, so if we just plot this thing, then the time period of this thing will be 2 pi upon delta by 2, which is 4 pi upon delta. So you are right about that. So now uh, what is happening over here is, and this other, just a moment, there is problem with my screen sharing. So the other sine wave will be basically, it will have time period of 2 pi upon omega plus delta by 2. So now when we superimpose this, so this has like amplitude like plus 1, between plus 1 and minus 1. So therefore it's, when we try to superimpose this, it's like uh, we are trying to superimpose one like, so if we kind of have a mirror image of this thing about the x-axis, let us say, so this outer envelope becomes like this, right? So this is the outer sine wave envelope. So you can see that this pattern, it is occurring twice in one cycle, right?
Yes, sir.
So the resultant sine wave is inside this. So if
So
you,
time period should be equal, no, sir, for this.
no, time period of, see, if that's what I told na. So if you plot this 2x cos delta t by 2 separately, it has a time period of 4 pi by delta. That is correct. But if we look at this sine wave, the resultant sine wave, uh, so this peak keeps on occurring like twice in every cycle, right? It does not occur once in, so if it occurs once in every cycle of this sine wave, so then it would have been 4 pi by delta, but actually it occurs twice, right? So then the time period of beat becomes, that's why it becomes half. So that's why it becomes 2 pi by delta.
So this second 2 pi by omega plus delta by 2, it is time period of what, sir? In this.
No, that is time period of this part only. This,
So in this wave representation, which wave has the time period?
wave representation in the sense.
So in this drawing, sir,
Uh-huh.
which wave has the time period 2 pi by omega plus delta by 2?
No, there is like, The inner one, the inner wave, you can say like the inner sine wave that has that time period basically.
Okay, sir. Okay. Okay, sir.
Yeah,
Yeah. Thank you, sir. Have
yeah,
a nice day.
yeah, yeah. Thanks for bringing up that. So any other questions that you had?
No, sir.
Okay. So I have uh, put together some set of problems which are related to the content for week 4 of this course. So, so I am actually planning to demonstrate how to solve those kind of problems. So before that, like we have one more participant, Luck DVT. So yeah, welcome to the session. So can you please uh, introduce yourself, please?
Yeah, good evening, sir. Myself, Vittal, from
Okay.
Hyderabad.
Okay. Okay. So the name in Google Meet actually shows something else. Yeah. Sorry
Yes, sir.
about that.
Yes.
Yeah.
Okay.
Yeah. 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 Please go ahead.
Sir, I am working for BHEL
Okay. Okay.
as
Great.
an engineer. So we
Okay.
are also visiting some project site where we come across all this signature analysis,
Okay.
address system, system one. So I am very interested to learn these fundamentals.
Okay, sir. So, like your background is uh,
Mechanical engineering from NIT Warangal, sir.
okay, sir. So you are like how many years have you been working in BHEL, sir?
Uh, uh, 14 years completed, sir, my
Oh, okay,
service.
okay, sir. Then you are a very senior person over there.
Yes, sir.
Okay, so on what kind of projects do you work over there?
Generally, we make the steam turbines, compressors, turbo generators. So
Okay,
whatever the equipment manufactured and supplied by BHL will be commissioned at various project sites like UPRVNL, AP
okay, okay,
Genco, TS Genco, Reliance.
okay,
So
okay,
and few overhauling projects will be also there. That like major inspection every 4 5 years, and sometimes they get some vibration problems.
okay,
During
okay,
that time, we visit and we will take some data with help
okay,
of some companies are there like Bentley, GE.
okay, okay,
So with help of them, we will take that data to our engineering,
okay,
and together we will give some solutions. What can be done to
okay,
resolve those issues? Whether it is looseness, rubbing, these kind of problems we encounter, and we give some resolutions. Sir.
okay, okay,
And your these basics are very useful for us.
okay, okay.
Generally, long ago we studied in BTech, na, so we are learning still.
Yeah, yeah, right, right.
Yes, sir.
Sure, thanks. Thanks for joining, sir.
Yes,
Welcome,
sir.
welcome to this online tutorial session. So my name is Parth Joshi. I
Yes, sir.
am currently pursuing PhD at IIT Bombay, and I am a recipient of Prime Minister's Research Fellowship. And as a part of
Okay.
that, I have got an opportunity to conduct these online tutorial sessions every week.
Okay, sir.
So you can watch the earlier. So I've been doing this sessions like since the last 3 weeks. So
Yes, sir.
please do watch the other earlier sessions. Like the recordings are available, sir, and
Sure, sir.
please do let us know your feedback on how like do you think they are useful, and if you have any further questions and or expectations, please do post in the discussion forum in the course, or like you can also email your feedback anything to me also. I can
Sure,
share
sir.
my email ID as well.
Okay, sir.
So, in your projects, what kind of like vibration related techniques that have you been used? Like, where do you use, like, what kind of things that you use?
Generally, we have got one system one, sir. That ADRE is there, na? Made by Bentley.
Okay,
Automated diagnosis for rotary equipments.
okay,
From that, we get that orbit data.
okay,
Uh, from the data, we will analyze what could be the reason. If it is 1x, 2x, some components are there, na?
right,
Single x due to unbalance. Whether it is a steam wheel, suppose if it is 0.5 frequency, then it may be oil wheel 0.4 to 0.5.
okay,
We will
okay,
basically, we are not go in depth, but we will tell customer that there are this kind of probability that it is arise due to these issues.
okay,
Based on that, we will again it forward to our engineering team is there, corporate R&D. It is in Hyderabad only.
okay,
So
okay,
they will also do some in-depth diagnosis on that data, and they will provide some recommendations. This may be the
okay,
probable reason. So
okay,
you have to open that steam turbine and check for that some fins will be there. Suppose it is based on that signature analysis, we come to conclusion that it may be due to the rubbing,
okay,
that stationary versus rotary blades may be touching.
okay.
So we will check that clearances, axial
Oh,
and radial clearances. That is one kind. Or this due to our bearing stiffness. Suppose it may be 0.5x component or 0.4x. So we'll came to know that it is due to oil wheel,
okay,
oil
okay,
lubile, that viscosity or due to some temperatures. So
okay,
they will
okay,
provide some more recommendations. In
okay,
this way, we used to give troubleshooting solutions, and we will attend that site issue also. We will take our crew. That system is again different. ADRI, we will conducting the signature analysis, and we are only assisting. We are taking some information and forwarding to our engineering groups. Again, performing that overhauling job. What to be done on that turbine
okay,
to minimize that vibrations or that issues, site issues.
okay, okay, okay. Great,
Mm.
great. Thank you, sir, for sharing your experiences. So, actually,
Yes.
you are talking about, like, when you say, like, in whatever you are like mentioning in terms of X. So you are mentioning about the frequency, right?
Frequencies, yes, sir.
Yeah.
1x,
So I think,
2x.
right, right. So I think you might be looking at, the signature. When you say signature analysis, you mean basically the frequency spectrum of the vibration signal, right?
Yes, sir. That border plot, orbit plot, waterfall plot. These we are come
Right,
across these things, and
right.
we are not having any certifications. With few basics, we able to understand something, and we will get it from engineering, analyzed through our superiors. Some expertise is there. GM level persons, separate department is there, sir.
Okay, okay.
It is corporate R&D.
Sure,
They,
sure,
they,
sure.
they have got all this, what we can say, establishment. Regularly, they are working on these machines. They will give us full guidance to us.
Right.
Based on that, their recommendation, we will troubleshoot the machine. We will open the machine. We will check all the clearances, and we will replace the new parts. We will do some retrofits. So finally, we will able to achieve, give the stabilized machine to the customer. We are basically like we are in service industry. Our
Right,
myself.
right,
Yes.
right, right. Sure, sure. Thanks. Thanks for sharing,
Yes, sir.
sir, and thanks for joining this session. So I
Yes,
hope
sir.
these sessions will be useful to you. We are covering some vibration measuring instruments related to this, but I'm not sure whether we'll be covering about this frequency spectrum analysis, but I think maybe we can connect later on. So I'll just share my email address in the chat, so we
Yes,
can
sir.
maybe connect offline.
We are using this transducer, sir. This piezoelectric transducer and
Right.
accelerometer. We are measuring the casing vibrations on gearbox, steam turbine, generator, and we
Okay.
are also using velometers. Similarly, we are also using for vibration measurement. MPUs, magnetic pickup units,
Okay, okay.
key phasers for speed reference, and LVDTs. So many, whatever you are explaining, na, those all are
Right, right.
we are seeing and we are working with them. This is very useful. This this
Sure,
lecture
sure.
and course is very useful for many of our.
Sure, sir. Yeah, thank you.
Yes, sir.
Thank you, sir. Yeah, so I think yeah, we will be covering some part of the fundamentals of these vibration measuring instruments, and maybe if possible, I'll also try to cover some part of this frequency spectrum analysis. Like you might be familiar with FFT, fast Fourier
Yes, sir.
transform, right? So like generally we use this FFT algorithm to process like we get the amplitude and phase. uh, we can like use accelerometers or other types of vibration measuring instruments, and then get the data, like capture the vibration signals from the relevant parts of the machine or system, and then process that data using FFT techniques, fast Fourier transform. Using that algorithm, by applying that algorithm, we can actually get the frequency spectrum, like the amplitude response as well as phase data. So hopefully, I think we'll try to cover that as well, if you are interested.
Yes, sir. Yes, sir.
Sure. Sure. Thanks. Uh,
Yes, sir.
so let me just start with the some small like problems related to the content for this week. So this week's content was about equivalent damping and related to vibration isolations and the concept of transmissibility. So I'll just share some examples related to that. Yeah. So let us start with a simple problem. So it is given that a vibrating machine is isolated from the floor using some springs, and it is given that the transmissibility ratio of the isolation. So it is 1.33, and so then the ratio of the frequency of excitation of the machine to the natural frequency. So that is being asked over here. So what does transmissibility mean? So let us say if there is some force acting on this system, and so if this, let us say this machine is connected to the foundation, and let us say this is the stiffness and damping of the foundation. So then the spring force and the damping force will be transmitted to the foundation. So the concept of transmissibility will be basically the uh, represent the magnitude of the force that is being transmitted to the total force. It represents the ratio of the force transmitted to the foundation to the total exciting force. So when it is given that this ratio is 1.33, so generally uh, we can find out that this transmissibility ratio comes out to be this thing, where zeta is basically the damping ratio and R is basically the frequency of ratio of the frequency of excitation to the natural frequency. So that is what we need to find out. So we have been given that this transmissibility ratio is 1.33 or nearly 4 by 3. Now here we have not been given any information related to damping. So let us assume that zeta is actually 0 because we have no information related to damping. So then the equation becomes one minus 1 upon r square is 4 by 3, or 1 minus r square is 3 by 4, or we get r square is equal to 1 by 4. So r is equal to half. So then therefore the ratio of excitation frequency of to the natural frequency is 0.5. So any questions? So if not, let us move on to the next problem. So in a single degree of freedom underdamped spring mass damper system, so it is given that when an additional damper is added in parallel, so the system still remains underdamped. Then which one of the following statements is always true? So when we add another damper in parallel, what will happen is that, so let us say if we have this damper, let us say C1, and we add another damper, let us say C2. So then the force acting on the system will be basically, so there will be two damping forces, so which will be C1 x dot and C2 x dot. So the effective damping will be basically C1 plus C2, so into x dot. So the effective damping is C1 plus C2. So the damping will increase, but it is given that even though we add damping into the system, this system still remains underdamped. So the C effective will be C1 plus C2, and we know that the transmissibility ratio is 2 zeta r whole square upon 1 minus r square. So now if we plot this, the variation of this transmissibility ratio with the frequency ratio, so if we substitute r is equal to 0, the transmissibility ratio will be 1, right? So if we plot the curve for transmissibility ratio, it will be of somewhat of a nature like this. So now if we increase the damping, so let us say this is for zeta 1, zeta 2, zeta 3, let us say zeta 4. So zeta 1 is less than zeta 2, less than zeta 3, less than zeta 4. So when we increase the damping, the transmissibility ratio, uh, so there is one frequency ratio, let us say R naught here, which at which there is some crossover that is happening. So this curve zeta 1, which appears to be the highest one over here, it becomes the lowest one over here, and here correspondingly zeta 2, zeta 3, and zeta 4. So for frequency ratio which is less than R naught, transmissibility ratio will increase with when damping will decrease. So when damping decreases, the transmissibility ratio increases, whereas when, why? Because we can see that when for the smallest value of damping, we see that the transmissibility ratio is highest, whereas when damping increases, the transmissibility ratio increases. So if we look at the options A and B, transmissibility will increase or transmissibility will decrease. We cannot say that with we cannot say that this thing, any of them is always true. So it is asked which of these statements is always true. So as we just saw that the transmissibility ratio, it actually depends on the damping ratio. So throughout throughout the frequency ratio curve, we saw that in some cases the transmissibility ratio will increase with increase in damping, or it will decrease with increase in damping. So statements A and B are not always true. The option C, time period of free oscillations will increase, and D, where time period of free oscillations will decrease. So let us check that. So the damped natural frequency will be basically omega n into root of 1 minus zeta square. So as we increase zeta, this expression will decrease. So root of 1 minus zeta square will decrease. So the damped natural frequency will decrease. So when the damped natural frequency decreases, the time period is 2 pi upon omega d. So when the damped natural frequency decreases, the time period will increase. So when damping will increase, time period will also increase. So the statement C is the correct answer over here. So any question? Then I think we can move to the next question. So when shaking force is transmitted through the spring, damping becomes detrimental when the ratio of its frequency to the natural frequency is greater than what. Uh, so this is in continuation with just what we saw. So we saw the plot of the transmissibility ratio. It actually changes its nature as the frequency ratio crosses this R naught value. So so when the frequency ratio is less than R naught, with increase in damping, the transmissibility ratio will decrease. Whereas when our frequency ratio increases R naught, the transmissibility ratio will increase. So that is the zone where the uh, damping becomes detrimental. So we need to basically find out this value of R naught. So R naught is the value for which transmissibility ratio is equal to 1. So we need to find out basically the so we need to solve this equation to get the value of R for which this is equal to 1 for all values of damping. So if we square both sides and multiply by the denominator of this both sides by the denominator of this expression, so we will get so this term is present on both sides, so we can cancel that. So our equation becomes 1 minus r square is equal to 1. So or we can write 1 minus r square is equal to plus or minus 1. So 1 minus r square is equal to 1 or 1 minus r square is equal to minus 1, which so this gives us r square is equal to 0 or r is equal to 0 basically, and r square is equal to 2. So which gives us r is equal to root 2. So for transmissibility ratio is equal to root 2. For the frequency ratio is equal to root 2. The transmissibility ratio becomes 1 and r is equal to 0 represents basically the point which represents this point, whereas r naught is basically root 2. At this point the crossover happens. So we can see that here in this graph, this is the plot of this curve from the some textbook. So here you can see that this root 2 is the point at which this crossover is happening. So we can see that when r is less than square root of 2, the transmissibility decreases with increase in damping, whereas when R is greater than square root of 2, the transmissibility increases with increase in damping. So that is the zone where damping is detrimental. So any questions till now? Any questions? Any doubts? I think we can proceed with the next question. So the value of displacement transmissibility for all values of damping ratio at frequency ratio R is equal to root 2. So we just found out that the transmissibility ratio is equal to 1 for all values of damping. Uh, so let us check that. So when if we substitute R is equal to root 2 in the transmissibility ratio expression, so we will get 1 plus 4 zeta square into 2 into 1 minus 2 whole square plus 4 zeta square into 2, which is equal to root of 1 plus 8 zeta square upon root of 1 plus 8 zeta square. So which is equal to 1. So this is verified now that the transmissibility ratio is equal to 1 for R is equal to root 2. Any question? Any question till now?
No, sir, you can proceed.
Okay. Okay. So we come to this next question. So it is given that a machine of mass 200 kg, it is supported on two mounts, which has each of them. So basically, those are springs. So each of stiffness K is equal to 10 kilonewton per meter, and it is given that the machine is subjected to an external force uh, f of t, which is 50 cos 5t. So we assume that there is only vertical translatory motion. So we have to find out the magnitude of the dynamic force transmitted from each mount to the ground. So to solve this problem, what do we have to find out first? We have to find out basically the amplitude as a function of the force and mass and stiffness. So first let us draw the free body diagram. So let us say x of t is the displacement of the center of mass of the machine. Center of mass of the machine with respect to its own equilibrium position. So then the two dynamic forces acting on it will be basically the two spring forces, and since we have assumed the displacement of the center of mass of the machine with respect to its equilibrium position, we do not need to consider the weight of the machine in the free body diagram. So then we can write down this equation of motion as mx double dot. So let us say this vertical direction is positive. So then we get F minus 2kx. So therefore mx double dot plus 2kx is equal to F of t. So the solution of this equation will have basically two parts. One would be the steady state oscillations because of the forcing, and the transient response because of the uh, natural frequency, because of the free vibrations. So let us first look at the steady state response, or basically the particular solution. So let us assume the solution of the form e to the power j omega t, and so therefore x dot will be j omega x e to the power j omega t, and x double dot will be j omega whole square x e to the power j omega t. So if we substitute this solution in this differential equation, we will get minus omega square x plus k x into e to the power j omega t. And since the frequency for the force is of a sinusoidal nature, we can assume the force to be, we can write down the force as f naught e to the power j omega t. So therefore x we can write down as f naught upon k minus m omega square. So this will be basically the amplitude of the steady state response to the forcing. So it is given that the forcing the amplitude of the force is 50. So F naught is basically 50, and the omega is equal to 5, and it is given K is 10 kilonewton per meter, so which is 10,000 Newton per meter, and the mass M is given to be 200 kg. So therefore X will become 50 upon yes. So X will be basically 1 by 100 meter or 0.01 meter or 10 millimeters. So this will be the steady state deflection of because of the forced forced vibrations. Any questions? Any questions till now?
No, sir.
Okay. So let us now look at the concept of Coulomb damping. So in Coulomb damping, the amplitude of the motion is reduced by how much in each cycle? So that is being asked. So let us take some spring mass system. So let us say if we take a simple spring mass system, uh, so let us say a mass is sliding over a surface that has uh, a coefficient of friction mu. So the forces acting on the spring, let us say if x is the displacement of the system, so it will be kx, and there will be the weight mg acting downwards, and there will be a normal reaction because of the surface, and the let us say if the velocity of the block, let us say if it is positive or if it is going in this direction, the friction force will be opposite to that. So the friction force will be mu n if the direction of the velocity is rightwards, and if the direction of the velocity is negative, or if it is like this leftwards, then the friction force will be rightwards. So the friction force changes direction when the direction of the velocity of the block will change. So now what is happening here is, like, let us say if we stretch the spring by some distance, let us say this is the zero position of the block, and if we stretch the spring by some distance x naught and leave the block, then the block will start sliding, uh, and let us say if the block starts traveling in this direction, then the friction force will be in this direction till the block comes to rest, let us say at some point over here. Till then the friction force starts acting like this. Now once this block comes to rest at this point, then the block starts moving again towards this direction. Then the friction force will become in this direction. So it is always opposite to the velocity. And in each cycle like this, so then when it comes to rest over here, it will come to rest, let us say at some point over here. So which is like after, so this x1 will be after one full cycle. So it will be less than x naught, definitely, because some energy has been dissipated because of the friction. So by how much? So that we need to find out. So as we just have seen, so we can write down the differential equation for one half of the cycle as mx double dot plus kx is equal to minus mu n when x dot is positive. So as we saw that when x dot is positive, this friction force is in this direction, negative direction, x direction, whereas when the velocity is negative, the friction force is in positive direction. So we will have two parts of the oscillation. So for the first half cycle, we can write down the solution in this form, whereas for the second part, we can write down the solution in this form. So let us say if we start with some initial conditions. So let us say if our initial velocity x at time t equal to 0. So the displacement at time t equal to 0, let us say that is x naught, and the velocity x dot at time t equal to 0, let us say it is 0. And just after releasing the block from rest, it acquires some small initial velocity. So so we are basically starting from somewhere over here. So this is x naught, and then it will start it will acquire some velocity in this direction. So we will be looking at this part of the solution for dx by dt is less than 0. So here x dot is negative. So we just after releasing the block, so that means the time t is nearly 0 just after time t equal to 0. So there won't be much displacement in that very short infinitesimal time. So if we substitute t equal to 0 in this solution, we will get x naught is equal to a3 cos omega nt, where if we substitute t is equal to 0 here, we will get x naught is equal to a3 plus mu n by k. So a3 we will get it as x naught minus mu n by k. And since we have been given x dot at time t equal to 0 is 0, if we differentiate this equation, we will get a4 is equal to 0 by substituting x dot at time t equal to 0 is 0. Now if we want to find out what is the extreme leftmost position that the mass can attain, so that will be after one half cycle. So what is the time period of the oscillations? It will be 2 pi upon omega n. So for one half cycle, which means time period, so time will be, so for time t equal to half of time period, so which is basically pi upon omega n. So if we substitute t is equal to pi upon omega n, then we will get x is equal to minus a3 plus mu n by k. So x will be minus of x naught minus mu n by k plus mu n by k. So we will get x at minus x naught plus 2 mu n by k. Now starting with this displacement as our initial condition, it will now acquire a positive velocity towards the right from this position. So now it has come to its extreme leftmost position. So then it will acquire a velocity x dot greater than 0. So then we will be looking at this solution now. So then we will get x dot at pi by omega n should be again 0 because the block comes to rest at that point. So it is basically, so a1 so this term will be 0 and this term will be minus 1. So minus a1 minus mu n by k is equal to minus x naught plus 2 mu n by k. So a1 minus a1 is equal to minus x naught plus 3 mu n by k. So a1 is basically x naught minus 3 mu n by k. So after one full cycle, so now we found out the value of a1. Now after one full cycle, which is time t is equal to capital T, what will be the x? So that will be, so T is equal to 2 pi upon omega n. So for that, we are looking at x of T, which is x of A1 cos 2 pi upon omega n into omega n plus A2 minus mu n by k. So here we will get, so this term is equal to 0 and A1 we have already calculated, and this term cos of 2 pi is equal to cos of 2 pi is equal to 1 and sine of 2 pi is equal to 0. So A1 minus mu n by k, so which is basically x naught minus 3 mu n by k minus mu n by k, which is x naught minus 4 mu n by k. So the amplitude reduction in one cycle, so it got reduced. So we started with some initial displacement x naught. So in one half cycle it reduced to 2 mu n by k, and in one full cycle it reduced to by 4 mu n by k. So in every cycle it will reduce by 4 mu n by k. So the correct option is amplitude is reduced in each cycle. So in each cycle amplitude is reduced by 4 mu n by k. So if we plot a graph of this, the same calculations that we did, so we can see that we start here with x naught and with initial velocity let us say 0, and and if we see that after one half cycle it reduced to x naught minus 2 mu n by k, and then in after one complete cycle it became x naught minus 4 mu n by k. So likewise it will go on reducing by 4 mu n by k in every complete cycle. So any doubts till now? Any questions? If not, like we can just have a quick look at how to use MATLAB to solve this kind of a problem. So let us say, if you want to visualize how the, if we want to find out how the response of a system with Coulomb damping for a forced vibration. So it is given that the mass spring mass system with mass is equal to 5 kg. The spring stiffness is given as 2000 Newton per meter. The coefficient of friction, let us say, is 0.5. So, and the force F varies as 100 sine 30 into t. So, if we can start with an initial velocity of 0.1 and initial displacement of 0.1. So, let us have a look at how the behavior can be using MATLAB. So, anyone of you are familiar with MATLAB?
No, sir.
Not familiar. Not familiar. Okay, fine. No problem. So it's basically like a tool which you can use to uh, do some mathematical calculations and mathematical modeling and simulation. So it is a very versatile tool which you can use for any analysis in any domain. So it can be a mechanical system, electrical system, or any kind of system. So you can use it to model the behavior of any system and analyze the response of the system to different inputs. So in today's session, I'll be just sharing uh, an example of how to use MATLAB to solve such kind of vibration problems using ODE solvers, which are basically a category of solvers in MATLAB, which are used for solving ordinary differential equations. So, like we are basically trying to model the behavior of our system in the form of a differential equation. So generally, when we are doing some kind of mathematical modeling, we are trying to represent the behavior using basically trying to uh, we are trying to represent our the behavior of our system using mathematical modeling and get the behavior in terms of a differential equations. So let us say if we have the spring mass damper system, and here in this is an example of a MATLAB code which I have written. So it is given that we have these are the parameters of the system, and we have this initial condition with which we represent in the matrix x naught, and the time span for which we are interested in looking at the motion. Let us say we want to look at the motion for the first 5 seconds. Then we can use the ODE 2.3 or ODE 4.5 solvers, and we will see the performance of these two solvers individually. So in this ODE solver, we need to give the differential equation of the system in a state space form, and so that is given over here, and that function is given as an input. The time span and the initial condition is also given as an input. So with this, if we try to run this script, we will see so we get this output in the form of this figure. So for forced vibrations, we can see that the because of the Coulomb damping, the system like the amplitude of the system is goes on decreasing, and finally it settles to a steady value. So if we increase the, let us say, the time span to, let us say, 10 seconds, and try to solve it again. So we can see that the amplitude settles somewhat after, let us say, 5 or 6 seconds to some kind of a steady value. And in the initial transient response is because of the Coulomb damping. Now if we want to look at the free vibrations, let us look at the second figure over here. So we can see that this amplitude is varying linearly. So we provide an initial displacement of 0.1 and an initial velocity of 0.1 and let the system go. So then we see that the amplitude decreases linearly. So in every once full cycle, the amplitude will reduce by 4 mu n by k. So we can verify that. So the amplitude has reduced by 0.07957. It has, so we will verify that. So our coefficient of friction was assumed to be 0.2. So 4 into mu into the normal reaction will be mass into acceleration due to gravity. So mass will be 5 into g into is 9.81 divided by k, which is 2000. So 0.0196. So we started with this amplitude. So 4 mu n by k is 0.0196, and we saw that after one cycle the amplitude reduced to 0.07957. So which is about 0.02. So both of them are quite close. So the difference between these two is because of the errors in numerical integration, but we can see that they are nearly equal. So this is how we can use MATLAB to solve the simple vibration problems like this. We can also use it to solve you can use it to solve like the vibration problems in case of uh, with problems with viscous damping. So let us say if we take uh, a spring mass damper system, and if we want to get the response of the system to uh, with so in case of viscous damping, if you want to get the nature of the response of the system, so we can model the system in this way. So depending on the uh, transient response, so it can be the response can be either under damped, critically damped, or over damped. So we can construct the solution and plot it in MATLAB, or we can also get a numerical solution of the differential equation using the ODE45 solver. So if we run this script, so we are setting the damping value as 40 over here, 40 Newton second per meter. So for a damping ratio of 0.1, we get the displacement of for forced vibrations. So it initially increases and then settles down to a steady value after a few seconds. So this is an example of underdamped system. So if we go on increasing the damping, so let us say instead of 40 we substitute it to 400, the damping ratio becomes equal to 1, which is a critically damped system. So the amplitude rapidly decreases and then it settles down to a small steady value, which is uh, like this. And now if we make the damping to be like 1000, then we can see that the response becomes something like this, where the system becomes very sluggish because of the very high damping ratio. And you can see that the amplitude of forced oscillations decreases very significantly. So it becomes about 0.001, 0.01, whereas here the amplitude is about 0.25. So you can see that how significantly the amplitude decreases because of the increase in damping. So I just wanted to demonstrate how you can use MATLAB to solve simple vibration problems. So let us now move on to our other set of problems. So any questions, any comments based on whatever we have done till now? So let us look at this example. So let us say if we have an aircraft engine, it is given that it has a rotating unbalanced mass, small m. Uh, so so it is given in this figure that uh, in one of the turbine blades, let us say we might have some kind of an eccentric mass, small m, and let us say the engine is rotating at a velocity omega. So then it is given that we can model the wing as a cantilever beam of uniform cross section A by B, which is shown over here. So we have to determine what is the maximum deflection of the engine for a speed of n rpm. So it is also given that assume the damping and the effect of wing between the engine and the free end to be negligible. So any idea how we can approach this problem?
No, sir.
Okay.
Maybe finding the equivalent stiffness for cantilever beam at
Yes.
point load. WL cube by 3EI.
Yes. Right. Yes. So you are right. So it is given that assume the effect of the wing between the engine and the free end, that is negligible. So we can kind of as like assume that the beam is only up till the engine. So you are right. So the deflection of a cantilever beam because of a concentrated load, so this deflection delta is PL cube by 3EI. So here I is basically the area moment of inertia. So in this case it will be B into A cube by 12 because the cross section is A by B. So this stiffness we can write it as P by delta. So we can write it down as 3EI by L cube. So which is basically the K stiffness. And then the force due to the rotating unbalance. So we can write down that. So like if we are looking at the uh, the oscillations in the vertical direction only. So we can write down the sinusoidally varying force as mr omega square into sin omega t. So we need to model this as a spring mass system. Let us say we can simplify this as a spring mass system with a force F acting. Uh, so this force we found out that is mr omega square sin omega t, and so let us say x is the displacement of this mass. So mx double dot. So that is the vertical displacement of the mass. So this represents the whole aircraft mass, the capital M thing. So that this free body diagram will look like this. So we can write it as mx double dot plus kx is equal to f. Is mr omega square sin omega t. So in general, we can also write it down as the f as f naught e to the power j omega t. And let us say we assume a solution x e to the power j omega t and substitute in this differential equation. We will get k minus m omega square x is equal to mr omega square So we will get x is equal to mr omega square upon k minus m omega square. So where k is equal to 3ei by L cube. So this speed omega for a speed of for the engine speed is n rpm. So that means that omega is equal to 2 pi n by 60. So we can solve this problem in this way. So with this, we have come to the end of the today's tutorial session. So any quick questions till now? Any doubts?
No, sir. Thank you. Very good lecture.
Sure. Thank you, sir. Thank you for joining. Thank you for joining this session. Uh, and I hope this session was useful to you. And
Yes, sir.
yeah, so if you have any questions related to the content of this week or any of the earlier weeks, please do post your questions in the discussion forum page in the online course website. Or if you have any specific questions or feedback for me, you can also email me directly. I have shared my email address in the chat. So
Yes, sir.
thanks again for joining this session.
Thank you
Thank
very
you.
much.
Thank you. We can close this session for today. Thank you.
Okay, sir.